This video is for section 6.1 on exponential functions, and an exponential function, EXP for short, exponential function has the form f of x equals, I'm going to use the letter b to the x power. B is for base, and the x is the exponent, but it's the variable x. And compare this to the type of function that we've already seen, the power function. I'm going to call that g of x, that has x raised to a power. So here's the difference, and this is why exponential function is a very different type of function. Here I'm raising this number, whatever the input number is, x, to a power p. X squared, x cubed, x to the negative 2, whatever it is. We're raising different values of x to that same value p. Now, with the exponential function, the variable is in the exponent. The base is fixed. So we'll have different inputs giving us different exponents. Same base. So that's kind of the reverse of this, but they're really not even that closely related. Some applications of exponential functions, and the reason that they're so important is they apply to things like compound interest, which in investment is, or in loans. Either it works the same both ways, whether you're getting money from your investment or you're paying extra money to the bank for having borrowed money. Compound interest means that the interest is computed not only on the original amount, but on the other interest as well. So it works for you in the case of retirement, and it kind of works a little bit against you in the case of loans or mortgages. Another application of exponential functions is population growth. And this isn't the only thing that governs population growth, but the more organisms there are of a particular type, the more opportunity they have to make more organisms. So I like to think of bacteria in the yogurt if I leave it out overnight. The bacteria there eat the yogurt and reproduce themselves exponentially. They make more bacteria, and then those bacteria eat more yogurt and make more bacteria, and that's another example of exponential growth. The last one I want to mention is radio decay or radioactive decay, and this is exponential decay. So the amount of a given radioactive material decreases over time. It degrades or decays. Also exponential, but not an exponential growth in this case. Like exponential growth of population or of funds or a balance in an interest-bearing account. That's exponential growth. This is the opposite direction. It's getting less and less over time. But the equations that describe it are of this form, a function where the base is constant, but the amount over time for these three, the amount increases exponentially or decreases exponentially. So let's look at a little bit how to work with these functions. I have an example for f of x equals 2 times 5 to the x. Find f of negative 3. So we're going to be evaluating this function. Now, that's the exponential part. The base is 5. The book used parentheses. It kind of helps. I don't want to have just 25 to the x. It's 2 times 5. You can put your dot there. So, f of negative 3, though, all I have to do is, like we've done with functions before, I need to replace the x with negative 3. And in this case, 5 to the negative 3 is, well, that's a negative exponent, so I'm going to put it in the denominator. It really means 1 over 5 to the third, 1 over 5 to the positive 3. And that is, just put the 2 in the numerator. 5 to the third is 125. So I plugged in the number in place of the variable, and then I simplified to get this, and that doesn't reduce. We'll do a few more examples in a second, but I need to introduce a number that comes along with exponential functions very frequently. This is called Euler's number, E. And it's approximately 2.71, but it is an irrational number like pi. Its decimal expansion keeps going and going, and it doesn't have a very obvious pattern. It's E for Euler, who was a German mathematician a few hundred years ago. There's actually other things called Euler's number, but this is the most common one. It's also called the natural exponential base. And it's used as a base for an exponential function. So here's an example that involves Euler's number. For f of x equal to e to the x. So it's that base raised to the x power. This is a simple exponential function. Find f of 3. So again, we're evaluating. This time, f of 3 is e to the, f of x is e to the x, f of 3 is e to the 3. That's actually it. That's the exact value. We can approximate this using a calculator. It's the e to the, it's e and a caret in the symbol. Oh, in the TI-36, it's e with a little box to the upper right. And you press that button, it gives you the exponential base. And you put in the number 3, and it should give you about 20.09. But in math, you're usually going to want the exact value, which is e to the third, and that's a very common constant. It's about 2.7 raised to the third power, which is about 20. Okay, and I've got another example that has a little bit more complicated algebra, or simplifying. This next one is not with Euler's number. This next one is to find f of negative 2 for the function f of x equal to 2.7 times 4 to the negative x plus 1 plus 1.5. So this is a little bit of a complicated functional expression. It's not just an exponential part. There's things that we need to do in the exponent and some other things. But according to the order of operations, I need to work with, well, parentheses first. F of negative 2 is 2.7 times 4 to the negative. Now I'm going to put in negative 2 in place of x. X, oh, that already has a negative sign there. It's negative 2. So negative, the first one from here, negative 2 plus 1 plus 1.5. And that's just a numerical expression. I need to evaluate it, but that's what we've done, is plug in the number negative 2 in place of x. What that gives me is 2.7 times 4 to the negative 2 is 2, plus 1 is 3. So this exponent here simplifies to 3, plus 1.5. 4 to the third is 64. And now, again, order of operations, I need to multiply before I add. So 2.7 times 64 is, I don't know what it is. I did this whole expression in my calculator. It's 174.3. And that is the exact value. It's not rounded or anything.